Okay, so today I am going to show you three small movies. So you have to just watch and enjoy. There is nothing. There is no use of brain. Such a beautiful thing, right? So, uh, and thanks to Professor Bush again from Louisiana State University, who allowed me to use his slides. Very good slides. Believe me, these slides are so good that before the exam date, you can just quickly revise the entire syllabus. Just maybe 1 hour, 1.5 hours. Such a nice. So basically, if I have to make these slides, it's very time consuming. So that's why I have borrowed these slides from him. So again, thanks. So today I am going to look at first languages. What is a mathematical definition of language? Okay. And language is very important. And you will see that all these computers accept certain kind of languages, I'm not talking about C, C++, Java. Those are high programming languages. Okay. But rather I am looking at very basic kind of languages for these four kind of machines which are possible there. Okay. So uh, as I mentioned in the entire uh, core thing about computer science, that there are four kind of machines. First is finite automata. Second is push down automata. Third is linear bounded automata, and fourth is Turing machine. Okay, so these four machines are very, very important, and we need to understand how they work, okay? And also how they process languages, what kind of languages they can accept, what problems they cannot solve, their limitations, capabilities, and so on. That is what we are going to learn in the next couple of lectures. I think this is the first one, probably next four more. So there are total 5 lectures on this topic. So first, today I'm going to discuss about the languages. Then I'm going to talk about one beautiful thing, which is DFA, deterministic finite automata, DFA, shorthand, DFA, and then NFA, non-deterministic finite automata. These three machines, these two machines, basically I'm going to look at it. But before that, I'm going to talk about languages. So you don't have to write anything also. Just enjoy watching the movie kind of thing, Just relax, and then watch. Okay. It's evening time, matinee show, right? So, okay. So languages. Language is a set of strings. So normally English language or whatever language you pick up, basically these are strings, right? Made of sentences, right? So these sentences you can think mathematically. We can say that language is nothing but a bunch of strings of over some alphabet. For example, English is, over the alphabet A to Z, right? A to Z. Initially, it was only 24. I mentioned to you earlier, right? So English there, or many other languages. And what do you mean by string? A string is sequence of symbols from alphabet. A sequence of symbols could be A, right? So the most beautiful language. Which one is the most beautiful language? Huh? What? The most beautiful is Chinese. Is a very symbolic. The most beautiful language I am talking in terms of is your own DNA. DNA, deoxyribonucleic acid, consisting of 4 letters ACGT. The most beautiful software that has built you. What kind of eyes you will have, what kind of ears you will have, everything is written in your DNA. Okay, so that is the language of DNA. Similarly, there is a language of protein, there is a language of all kind of things. So a sequence of symbols. So, for example, strings cat, dog, house. These are some words in that language anyway. So we will focus in most of the time. We will focus on alphabet A, comma B, having only two symbols, A, comma B. Alphabet is having only two symbols, A, comma B. So alphabet is a set of symbols. Normally we consider only this. A string is a sequence of symbols from the alphabet. So A is a string, right? AB is a string. ABBA is another string, right? All these are examples of strings over the alphabet A, comma B. Okay, there are two symbols A, comma B. So now there are, we call it as a string variables. U is equal to AB, V is equal to this thing, U, V, W are the variables, string variables. Anyway, decimal numbers alphabet. So these are also strings, right? If you take binary numbers alphabet, these are binary strings. Most fascinating for the computer science people, you should know what is binary strings, right? You know all your PDF file, doc file, whatever file, Excel sheet, you can convert into byte strings. Byte strings. So those strings over the field of 256 number of elements, right? 2 raised to power 8. So in order to construct field with 256 number of elements, you require degree 8 polynomial over Z2. If you remember, all those beautiful things are coming in place anyway. So that is a binary. This is very useful unary number alphabet. Unary numbers 1, 1, 1, 1, 1, 1. So all these 1, 2, 3, 4, 5 is certain number of ones. This is useful for programming Turing machine. You will see that Turing machine can be programmed nicely with when we assume alphabet is unary. Unary alphabet means only one symbol, one. Everything is written in terms of ones. Okay. So that is unary alphabet. Now we can do certain string operations. Once we define strings, so collection of strings is a language, right? If we take two strings, then what we can do with them? We can play with them. Take one string, take another string, and you just do concatenation. So if V is this string, W is this string, concatenation is, you can just combine them, A1 to AN, B1 to BM, right? Concatenation of the two strings. Okay? Very simple operation. What else you can do? Reverse. If there is a string A1 to AN, or something like this is an example, you can reverse it. So AB, AB, A, B, B, B is nothing but B, 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 A, then BA, BA, right? Reverse. Reverse of the string. Please stop me at any point, ask me questions. I love interaction more. Since there are very few people today, I may give you a surprise quiz towards the end, right? No? You can send SMS to your friends, they will come back. Anyway. So, string length. So basically, if there is a string having n symbols, so length is number of symbols. Okay, so n here. Here the length is 4, length is 2, length is 1, right? Very easy. Length of a string. Length of concatenation is sum of the corresponding strings, right? So concatenation UV, length of concatenation of U and V is some length of sum of U and sum of V, I mean sum of U and V. If U is this, A, V is AB, AAB, so then size of U is 3, size of V is 5, and size of concatenation is 5 plus 3, 8. These are very easy concepts, right? Now come to this empty string. This is sometime, it will give you some confusion after some time, you will see. So carefully watch. Empty string. What do you mean by empty string? A string which has no symbol. Okay? A string which has no symbol. And I call it by lambda or epsilon. Okay? We denote it by lambda or epsilon. So obviously, size of lambda is 0 because it has no symbols. Okay? And you can concatenate lambda on other side of a given string, you will get the same string. Right? Which is obvious because it has no symbol. Right? Okay, substrings. So raise a hand. I think Parik. I don't know whether if I can listen to him. Yes, can you unmute yourself and say something, whatever you want to say? I don't know what is happening anyway. Substring. So if a string is given like this, any subset of symbols, right? So like A B B is a, is one substring, right? Or here A B B A is a substring. Here, sorry, A B is a substring. It is only up to this. A B is a substring, right? B is a substring, or B B A B is a substring. Very simple concept, substring. Prefix and suffix of a string. If a string is given as A B B A B, so prefix is lambda, empty string, and the suffix is the whole. So basically, you can break any string into two substrings. One is prefix, another one is suffix. Okay. So here, similarly, prefix is A, and rest of them B, B, A, B is suffix, and so on. It's very easy, right? Prefix and suffix. Now you can do another operation. Take a string lambda, and you can concatenate it with itself n times, and you can write it as W raised to power n is equal to W n times concatenation, right? So, for example, ABBA whole square is ABBA. And this by definition or notation, W raised to power 0 means empty. A string with no symbols. Makes sense actually, very natural choice. Then this is a beautiful operation, star operation. Set of all strings that are possible from a given alphabet A, comma B. So that means strings of length 0, strings of length 1, strings of length 2, strings of length 3, all possibilities. So what could be? You can see that if sigma is A, comma B, this is a string of length 0, lambda string, empty string. 1, there are only 2. 2, there are 4. 3, there will be 8, and so on. Sigma star is strings of all possible lengths over alphabet. Sigma is equal to A, comma B. Plus operation. So just like that, we define sigma star. If sigma is equal to A, comma B, sigma star is all possible strings. Sigma plus all strings except the first string, the empty string. The empty string is not there. We take that thing out. This is sigma star. Sigma plus is sigma star minus empty string. These are the convenient notations we will use quite often. Okay. So what is a language? A language over the alphabet sigma is any subset of sigma star. Very nice. Sigma star, all possible strings. Bunch of strings from all possible strings will be a language by definition. Right? Sigma star, all possible strings of all length. So if you take only portion of it out of that all possible strings, that will be a language. So basically any subset of sigma star is a collection of strings, which will be nothing but a language. A language over alphabet sigma is any subset of sigma star. If sigma is this, sigma star is this is a language consisting of lambda. This is a language consisting of 3 strings. This is also a language, right? So bunch of strings taken out of all possible strings is nothing but a language. This is a little bit unusual example of language, infinite language. L is equal to A and B n, where n is non-negative. So n is equal to 0, it will be empty string. Then n is equal to 1, it will be AB, then AA, BB, and so on. Right? You can see that clearly. BBA, BB will not belong to this set, right? Because it has to be equal number of A's and equal number of B's, right? In certain number of times, right? Those will belong to L. this we can leave. All this we can leave anyway. This is कभी कभी कंफ्यूजन होता है यहाँ पे, राइट? तो अब मेरे को बताओ इसमें what is this empty language? Language with no string. And what is this? Language with empty string inside. Empty string has no symbol, that is fine. But that language contains empty string. See the beauty? Right? And size of element. So what is the size of this? 0. Nothing is there. Whereas size of this is 1. Right? There is one string, which is empty string, which has no symbol. And so on. These are two spatial languages. So note that y is equal to this empty language, which is not equal to language containing empty string. Correct? And size of this is size of phi, which is 0. Size of this is 1. And size of empty string is 0. Because that empty string has no symbol. Size of that will be 0. Right? This is clear? इसमें कई बार कंफ्यूजन होता है आदमी को, राइट? थोड़ा सा भी चूक गए तो गलती की संभावना रहती है, राइट? फाइन. Now we can do certain operations on these languages. We have defined operations on the strings, concatenation and so on and so forth. We can talk about operations on these languages. Language is nothing but a subset of sigma star. I'm assuming sigma is equal to a comma b, and language is simply a subset of sigma star, right? You can take any alphabet sigma. That's okay. So union of two, all these user set operations, union of two languages. Union of two strings, right? I mean, the two collection of strings, intersection, minus sign, complement of a language, L bar is sigma star minus L. All those strings in which are left in all possible strings of all length minus L, right? That is this. Reverse of a language. Reverse of a language is all those strings. So L is a language which will contain some strings W. So reverse of L will be WR for each W in L. So take everything and take reverse. Everything is reversed in that set, right? For example, this is there. The reverse of this whole thing is reverse of every string. The reverse of this is reverse this thing BN AN, right? Concatenation of two languages. If L1 and L2 are two languages, so all possible ways you can concatenate, right? X, Y, such that X is in L1 and Y is in L2. So for example, if these are two languages, this and this, you can concatenate A, B, A, then A, B, B, A, B, A, then B, A, B, B, A, right? All possible ways. It's a बहुत आसान है actually, such a nicely written. Another operation, so we have talked about take a string and raise it to the power n, W raised to power n. Now we can talk about if a language is there, you can concatenate language L n times. L raised to power n can be defined. L raised to power n is L concatenated n times. So AB cube is AB, and you can. Again, the special case L raised to power 0 is singleton lambda. Lambda is the empty string. Clear? Okay. सब trivial है. The star closer is known as clean closer. Clean star. Clean was a scientist. So all strings that can be constructed from a language L is known as clean star. So L star is equal to L0 union L1 union L2. So L0 L1 L2 means LL, concatenation of L twice, and so on. For each language L, you can compute, right? This is straightforward. Similarly, you can define positive closure L plus, where the first one L0 is not there and everything else is there as a union. Oh yeah, part 1. Now you need a break, right? 1 minute break, tea break. We don't have tea here. So कितनी देर लगी है? 15 minutes maybe. So now we look at the second part of the movie, which is another beautiful thing, deterministic finite automata. And then we will talk a sister of DFA, which is known as NFA, non-deterministic finite automata. So DFA is essentially, as I mentioned in the previous class, is the brain of your vending machine or the brain of elevator. You know, it's very, very useful concept, very useful in speech processing, signal processing, speech processing, all these technologies that you see, right? They have beautiful applications of these concepts. So let me start the first one, deterministic finite automata. जब ready हो जाना तो मेरे को बताना. Ready हो? So you can clear your thoughts, जो कुछ देखा है उसको भूल जाओ, 1 minute के लिए आंखें बंद करो, ऐसे सांस लो, and then you are ready, right? So we can. Again, thanks to Professor Bush. So, for these slides, and so we are now going to cover deterministic finite automata. So basically, we know what we learned in the previous slides: language, string, operations on string, operations on languages, right? What kind of operations are possible, right? And certain symbols and introduction. So deterministic finite automata is the simplest form of computation that is possible. And these machines do not have any memory. They are without memory. So basically, what you have, there is a tape, input tape. So string you give as an input. There is a finite automation. There is a machine. This is the core part of the machine, which will process the thing. And output is either you accept the string or reject the string. So the task of the machine is to either accept the string or reject the string. Okay, this is a very simplest form of machine. So let me look at some more details. So this machine can be described by what is known as transition graph. So transition graph, so there will be initial state of the machine. So these are states Q0, Q1, Q2, Q3, Q4. How many states are there? 5 states are there, fine. Then there is one initial state from where everything will start. Initial state is normally denoted by this symbol, initial state. And then at least there is one final state. There could be more final states as well, but there is at least one final state like this, double circle. Final state, which is accepting state. So it will be clear what is the meaning of that. These kind of arrows are known as transitions state. This is accepting state. In fact, there are 1, 2, 3, 4. How many? 5, 6 are six states are there, right? Okay. So now, question is, what are these AB? AB are symbols from the alphabet, right? So one very striking property of this automata is, for each state, I should know where to go for each input symbol of the alphabet. If the alphabet is sigma is equal to A comma B, I should know what I should do. If you pick up any state in the system, if you are in any state, you should know where to go after receiving A. You should know where to go after receiving B, right? That you can verify. This is a very important property of the deterministic finite automata. Each state has a transition for each input symbol, right? You need to define this. Okay. So let us see some. So this is the property which I mentioned. For every state, there is a transition for every symbol in the alphabet. For example, if you are at Q0, if I receive A, I know where to go. If I receive B, I know where to go. You pick up anything. Suppose I am here. If you receive A, you go here. If you receive B, you go here. If you suppose you are here, if you receive, you come here. A, if you will come here. If you receive B, you will come here, and so on. For each state, whether it is initial state, accepting state, final state, or in any intermediate state, For every symbol, I should know where to go. This is the key property of deterministic finite automata. Got it? For every input symbol, you should know where to go. Now let us see. On the input, initial configuration is A, B, B, A. And we are starting everything from state Q0. So what will happen? You read A from here, go here. Then you read B, you go here. Read B, go here. Read A, go here. Right? This string will be accepted. Right? The string A, B, B, A will be accepted because we started from there. I'm not worrying about Q5. What happens? I will accept a string if the entire input is consumed and we are in a final state or the accepting state. And we will consume the string. Okay? So we'll accept the string. So here is the thing. Q0 A, after receiving A, you go to Q1. After receiving B, you go to Q2. Another B, you go to Q3. Another A, you go to Q4. Accept. Input finishes, and you are in the final state. So last state determines the outcome that we should accept. कुछ लोगों को नींद आ रही होगी वैसे. By the way, what about this? Anyone tell? A, B, A. If you receive A from here, you go here. Receive B, you go here. Receive A, you are here. Are you going to accept this string? No, because we are not in a final state. We are somewhere in between, intermediate state, right? So this string is rejected by the automata. Automata is this machine, is going to reject this input, right? Got it? Very simple. See? After receiving A, you go to Q1. After receiving B, you go to Q2. After receiving A, you go to Q5 and reject. Input is finished and you are not in the final state, so you reject the input. Okay? Tape is empty, having only empty string, Then what will happen? No symbol to read. No symbol to read. You are here, no symbol to read. So what? पढ़े रहो वहीं पे क्या फर्क पड़ता है, right? And so basically you reject, right? You don't have to move, nothing to read, right? Fine. I think in the evening we should allow tea, right? But they don't allow tea here, right? Should sit. Normally in my classes no, I can't allow. You have to. What I'm saying that normally in my classes, when I was in US, people used to drink tea, coffee, enjoy the class, rather than anyway. So this automata accepts only one string, which is ABBA, right? ABBA. You saw that it is accepting, right? So there are a couple of problems that people study. Given a automata, somebody will give you this diagram, fancy diagram, and somebody will say that please find out the language accepted by this automata. If you want to try some of these things, take a cup of coffee and try homework number 3. You will get a lot of things. Another problem is, given a language, construct an DFA which can accept the language. That's another problem. DFA दिया हुआ है, language बनानी है, that is one problem. Language दी हुई है, DFA बनाना है, that's another problem. So you need to have this practice, and the practice will come when you do the assignment number 3. Okay. So we have enough problems for you, but I will show you some examples how to do these things. So to accept a string, all the input string is scanned and the last state is accepting state. To reject a string, all the input string is scanned and the last state is non-accepting state. Fine. Another example. Lambda AB, AB, BA. This is the language. Now you see here, there are 3 accepting states, this, and this. There could be multiple accepting states. That is fine in the deterministic finite automata, no problem. More than one accepting states are okay. Okay. So that means when we have more, so what happens? Empty string will be accepted, right? Empty string will be accepted immediately. AB will, what happens to AB? A and B accepted. And what about AB, BA? AB, BA, A, B, B, A accepted. All these three strings accepted, right? Got it? So these kind of problems will you get into, you given a language, construct the automata machine you have to construct. Given the machine, construct the language. This is a very beautiful problem, right? Now, empty string, you see, accepted. What about this? If you see in this one, AAB, A, another A, and B, accept, right? This will be accepted. Relation case, BAB, B, A, B, reject because you are not in the accepting state, right? So the language accepted by this is A and B. Any number of C, this kind of arrangement, this loop makes it possible that any number of A's can accept and then finally B and you accept. So A and B will be accepted, right? Any number of A's, doesn't matter. 100 or 20 or 10,000, it doesn't matter, right? You keep on self loop, use the self loop, and then you absorb. Another example, here the alphabet is sigma is equal to 1, single element, and this is even. All even strings will be accepted. So I leave it as an exercise for you, tea time problem. Sometime you can do that, right? So formal definition, after giving these many examples, and after that I am going to give you one or two more working examples. I will do it here so that you understand. धीरे धीरे से चीजें समझ में आ रही है ना? Slowly जाना है, तेज नहीं भागना है, right? Anyway, so full system consisting of Q set of states, user, sigma input alphabet, delta transition function. I have not talked about transition function. Q naught initial state, F set of accepting state. You know, there are bunch of accepting states possible, final states possible. In this example, Q is Q naught, Q1, Q2, Q3, Q4, Q5, right? All states. Fine. Input alphabet never contains lambda, that is fine. Initial state, Q naught is there. Set of accepting state, there is only one here, right? Which is Q4. Only one. You can see that Q4. Okay. Transition function we can talk about. What is transition function? So this actually making these pictures is a difficult. Every time you make a picture, means you have to draw pictures. You should be good in paintings, drawing. So mathematicians, what they even talk in terms of functions. So you don't have to draw pictures. So we can say that if you are in a state Q, after receiving symbol X, you go into a state Q prime. That's what is happening in general. Every time you are in some state, you accept some symbol and go to some state. That's what is happening all the time, right? This is the most generic thing that is happening. So we are saying that you are in a state Q. After receiving input symbol X, you go to state Q prime and you denote it by delta Qx is equal to Q prime. This is known as transition function, delta. Okay. So this describes the result of a transition from a state Q with symbol X. For example, delta of Q naught A is Q1, right? लिख सकते हैं, right? Next one, delta of Q naught B is Q5. Delta of Q2B, Q3, right? So everything can be described. All these transitions can be described by this table, and this is the program for running this. If I ask you write a program in C, Java, C++, Java++, whatever is available to you, right? So, right. If it is not available, you can create one anyway. So you can write this table, right? So table management is easy for you. This captures the entire scenario. Now this table tells you if you are in some state, no matter which state you pick up, after receiving symbol A or B, where to go, it is telling you. This table is telling you, right? This transition function business captures the entire business of finite automata, right? Got it? Simple thing, beautiful thing, right? So I need to little bit extend this transition function definition. Right now it is acting on single symbol. What happens if you have a string? So basically that will also make our job easy. If I can define delta on strings, and that is how what we can define is known as extended transition function delta star. We are in state Q. After receiving string W, I go to state Q prime, right? This can be decomposed into basically a lot of delta functions in between. Okay, so let me show you that. So delta star Q naught AB is Q2. You are in Q naught state, string is AB. So AB, you go to Q2, right? Extended transition function, delta star. Similarly, delta star Q naught A is Q5. Right? Clear? Delta star Q1 BBA is Q4. You can see that. A special case, when you receive lambda, of course, you remain the same state, right? Q. So essentially, in general, any extended delta transition function implies that there is a walk of transitions, intermediate states through some intermediate state. That's what you are observing here, right? So language is accepted by DFA. Language accepted by DFA is denoted by L of M. M is the DFA. So contains all the strings accepted by M. So we say that M recognizes the language. Okay. So for a DFA, language of M can define mathematically all those strings in sigma star. Okay. Such that starting from the start state, for all those strings W, delta star belongs to one of the accepting state. Right? F is the set of accepting state, it belongs to one of the accepting state. That is how we define the language of the automata. Right? I think now there is a time to give you some examples. And similarly, there is a language rejected by is a complement. It does not belong to any of the accepting state. Now see the beauty. This is empty language. And which machine will accept it? Empty language. Why is this is empty? This machine will do the job for you. No accepting state, right? Right? A beautiful relationship. Similarly, you see here, make is accepting and put an arrow with all A comma B. कुछ भी डालो A, B का any combination, A, B, 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 whatever, it will accept everything. Sigma star. Any string in sigma star will be accepted in this machine, right? Fine. Any question? So basically, I'll give you a few more examples, and I think then we are done. We'll be done with NFA. Language of the empty string. Now I am going to ask you one question, and it's a beautiful question. If I delete this portion here, suppose I don't have this, don't you think this is going to work for empty string language? If language is empty string, only this symbol is going to work. क्यों भाई क्या सोचते हो? Is it going to work? Empty है, हमने accepting बना दिया, काम खत्म. हाँ? नहीं, ये lambda है ना? So I am saying that, this is accepting. Lambda has no symbol. So if suppose we don't draw this picture, this portion is not there. So what will happen? This will accept lambda, right? So our job is done. Why do we need this? Yes. What happens when you receive a symbol A or B, right? Remember the property I told you in the beginning? For each input symbol A or B, you should know where to go in each state. So here we cannot draw only this. Then I have to draw another state. Looks like a extra state, but that's fine. And for A, you go here. For B, you go here. But once you draw this, you should tell what will happen if you receive A or B here. एक ऐसे डाल दिया arrow. Got it? Right? Nitty-gritty things I am telling you. It's minor. Otherwise, जरूरत क्या थी इसकी, right? But because we have the property that every state, whenever we are in any state, we should know where to go after receiving input symbol A or input symbol B. Where to go, we should know. Since that was not there, if we draw this portion, then that will not be a DFA. Okay? DFA has this property that no matter which state we are, we should know where to go after receiving symbols A or B. Right? Okay. So this example will be enough for you to understand DFA. So this kind of problems are given in homework number 3. Language is given, all strings with prefix AB. So all those strings which start with AB and rest of thing I don't care, whatever they are, in any order of A and B, I don't care, right? If I want to accept this, how should I make the automata? So gehri saans lo and then you can watch. We start with Q0, start state lagaya, right? This is start state. Then I should know where to go after receiving A, after receiving B. और हमको एक्सेप्ट क्या करना है कि ए बी शुड बी देयर, राइट? प्रीफिक्स ए किया हमने, बी किया और इसको एक्सेप्टिंग बना दिया, राइट? ए बी हो गया. नाउ ए बी, आफ्टर ए बी देयर कुड बी एनी कॉम्बिनेशन ऑफ ए एंड बी, आई डोंट केयर. सो इन लास्ट वन आई हैव एडेड दिस एरो लूप ए कॉमा बी, right? In any order, whatever way it comes, this will absorb those things. And this A and B is accepted here, right? So A, B. So this portion looks like is going to do the job for you. But why do we need this? Every symbol we should have a, for every state you should know where to go. So from here, I have told you what to do if you get D. But what happens if you get A? So एक और डाल दिया हमने Q3, right? Similarly, यहाँ पे A का तो बना दिया था. B I will put it here, and like this. Now here, then again I need something from here. What happens if you receive A comma B? एक और loop डाल दिया A comma B. This is how we construct the DFA from the language. Understood? Clearly? Right? This kind of problem you have to do in your homework number 3. Take a nice pen, a nice seat, chair should be nice, comfortable, and a cup of coffee in the evening, and start working. Got it? So I think after that there are 1 or 2 more examples which I'll give you as a T problems. I am not going to do it anyway. So I think all binary strings containing substrings 0, 0, 1. So you need to think about the logic. Okay, answer is given to you. Delete this answer and think about it yourself. All binary strings without substring 0, 0, 1. What to do? All strings which are ending and beginning with A. This is a beautiful automata, right? So a language L is said to be regular if there is a DFA that accepts it. The language accepted by DFA is known as family of regular languages. So all languages accepted by DFA are known as regular languages. I'm going to talk about it, detail about it later on, but that's all about DFA. There are all these examples, A, B, B, A, this. These are examples of regular languages. So there exist DFAs that accept these languages. Right? That's why these are known as example of regular languages. So question comes, are there languages which cannot be accepted by DFA? Answer is yes. And that answer is given in the next slide. A and BN. Now, anyone thinker in the class can tell me why DFA cannot accept this A and Bn. This language A and Bn, equal number of A's, equal number of B's. क्या हो गया? सबको सांप सूंघ गया जैसे? Can you construct DFA, deterministic finite automata, which can accept? Remember, deterministic finite automata, first of all, first word is deterministic. We have deterministic choice for each input symbol, where to go. Finite automata means number of states are finite. It's another requirement. Number of states are finite. These two important things are there in DFA. Right? Now, should I give you the answer or leave it as a T problem? T problem. I think what I will do, I will leave it for you. Maybe in the next class, I can tell you why. Okay. Think about it. Why we cannot construct DFA. It's a very interesting and striking thinking. Thinking is important. I am not worrying about your answers. Remember, in exams also, I am not worrying about your answers. You may get right answers, but you will get 0 marks if your thinking is not correct. Okay. And if your thinking is correct, you got a wrong answer, but you may get full marks. That is a possibility. Don't think like, okay, so I look for thinking, your brain. That is a capital for me, right? Use your brain and then do something, okay? So you will see that what kind of problems are there when you try to construct a DFA for A and Bn language. Okay? A and Bn. कितना टाइम है और कुछ कवर करना है? थोड़ा हैवी हो गया? हैवी तो नहीं हुआ लेकिन चाय की कमी है, that's the problem. Evening time there should be tea. Okay, so in the next class, I am going to talk about non-deterministic finite automata. Since then, I mean, till then you can start working on homework 3, some problems related to DFA you can handle. Okay, thanks.